we're going to get started. All right. All right. Hello, everyone, and thank you for giving me this opportunity to present to you tonight. Today, we're going to be talking about embedded Rust. We're going to be talking about Rust running on a variety of different microcontrollers. And this is a little bit about me. I am effectively a full stack developer. So full stack developer has a bit of a, not really the correct term because I do embedded as well. So full stack usually implies front end, back end, database, but somebody is also on the actual hardware. There isn't really a term for that. So I'm all of that. I'm the tech lead at Hack Hunter. I actually have some colleagues over here, some good friends and colleagues. That's Sam and Mike. And we work together and we do a lot of security hardware. And I'm responsible for making sure that the stuff doesn't fall over. So so far I've been very lucky. So yeah, that's a bit about me. I've been developing for about 21 years now. Started out as a C developer, doing Motorola microcontrollers, then went over to SharePoint and did a lot of document management system and web development for a long time, and somewhere in between now at the moment, between sort of React and JavaScript and Rust. All right, so what are we going to be doing today? We're going to be talking a little bit about how do we get Rust on a chip. That's kind of something that's a little bit new. All right, we've got this thing called a Hall, which is a hardware extraction layer. We're going to basically be talking about that. Then we're going to be looking at four different types of microcontrollers. We're going to be looking at the STM32, which is a very well-renowned microchip or microcontroller. We're going to be looking at the ESP32, which is one of my favorite microcontrollers. And then we're going to be looking at a little bit of an Arduino, because everybody loves Arduino. And then we're going to be looking at the new Raspberry Pi Pico. So let's get on with some presentation. All right, so why would you want to basically use Rust in a microcontroller? Okay, it is a bit hard. It's very new. It's not as easy as it should be just yet, but there are massive benefits to using Rust. Okay, anybody who has looked up Rust knows that it's memory safe, right, which has massive advantages. Just by the way, I actually run an online course for ESP32 using C called Learn ESP32. And I basically use the what is known as the IDF, which is the IoT Development Framework. It's all C-based. And right, I can tell you now that all of the errors that my students come to me and say, this application doesn't work, 90% of the time, if you look at it, it's a wild pointer, it's index overflow, it's essentially, something's gone wrong with memory, and Rust basically guards us from that. It basically stops us from compiling those sort of bugs. So there's massive benefit in that, because I actually cost a company many years ago quite a bit of money by having a bit of a wild pointer. So yes, that's time for another story. So yes, it's memory safe, right? It's got a very strongly typed system, okay? And I'll give you a demonstration about this a little bit later when I'm showing you the ESP32. One of the things that you might find on one of these, on the ESP32 is that they've got pins on there that are only allowed to be used as inputs. They can't be used as outputs, all right? These are the higher ordered pins. I think it's 35, 36, 37, 38. Right? You can't use them as inputs. Now, in C, you could very easily basically index that particular GPIO and set it to an output. Of course, what happens is absolutely nothing, or your programs crash. In Rust, you can't even compile it. So it gives you type safety over the architecture and the makeup of your chip, which is pretty interesting and pretty unique. Okay, and then of course there's no garbage collection. Okay, so one of the things that people have been sort of going towards is a lot of Python these days. Okay, they're running Python on microcontrollers as well. The problem with Python is that it's, aside from it being not native, it's basically interpreted. It also has a garbage collector, like JavaScript also has a garbage collector, like C# also has a garbage collector, like Java has a garbage collector. You can't predict when the garbage collector is going to kick in and start cleaning up your memory. And at that particular point in time, you don't have control over the chip. The chip will do what it needs to do to clear its memory. And if the person is basically in a accident and you need to basically deploy the airbags for a car and it's doing its garbage collection, well, tough, like the guy's going to wind up with a broken nose, and that's just it. So, we don't have garbage collection in Rust, but we also have the memory safety, which is pretty cool. And then, of course, native speed. It's close to C or just as fast as C and C++. Okay, so how do we get Rust on a chip? All right. So just to put the premise over here, I'm a bit of a neophyte. If you don't know what that means, it means I'm a novice. I don't write a lot of Rust. I'm trying to get my head around it. I'm still getting into it, okay? But I've been spending the last couple of while just trying to figure out how this whole thing fits together. And that's essentially what I'm trying to basically portray to you today. There's this guy called LLVM. Has anybody heard of this guy? A couple of people? It's one of the more interesting technologies because this guy over here is effectively reshaping our world, and most people don't even know it. It is a massive technological advance. Right, this guy is basically enabling a lot of new compilers to come out of the market and target a lot of different architectures, including Go, including the new Carbon, including Rust. Rust was built with these things. So why do I have this slide over here? Well, basically, this is essentially how Rust gets put together. You have LVM, which is essentially a C++ compiler, and you produce the Rust language with it. And it basically compiles down to something called HIR, or high-level intermediate representation. It's kind of like a pseudo language or an intermediate level. It's like a virtual language. And what that basically means is the LLVM engine will basically know how to interpret that into multiple different architectures. So this is important for us to understand as embedded developers, because effectively what that basically means is that we can basically get Rust targets, okay? So there's a command that we can run. I'll just show this to you now. All my various different shells. Yeah, I got a collection of them, as you can see. So we got this thing called Rust Up. Right, so Rust Up, I'm assuming you've seen that when you've installed Rust, right? The Rust Up is essentially the utility tool that allows you to install stuff. And we can go target list. Now, if you do this on your machine, you might only find that you wind up with half a dozen. I have quite a few more because I've been playing around and experimenting with different things. And this is how we do it. You see, when we basically write a Rust compiler, or sorry, when we write an application, we can then specify a flag to say, I want you to target ARM32, or I want you to target the ARV microcontroller, which is the Arduino, or I want you to target the ESP32. So in order for us to actually compile to a particular microcontroller, we need to have we first need to have the correct target in place. So LLVM comes in and essentially produces a bunch of different targets, and then we can basically download those targets onto our machine. And this gives us the capability of actually producing raw Rust. Okay, so we can compile raw binaries into a language that microcontroller can understand. Now, if you've ever played with microcontrollers, the first thing you basically do is you open up a 1,000-page document, and you basically figure out which of the 100 pages out of those you need to understand. And then you figure out what registries do what. So if you want to basically switch on an LED, you're going to need to find out what registry it is. Then you basically find out which bit, and you flip the bits on and off. Okay, and then when you want to clear it, you don't go to that, but you go to that, but and then essentially, it's like, it's quite a bit of sort of intense sort of manual work, but it gives you a starting point. Okay, so once you've actually done that, you can then write Rust like this. Now notice a couple of things over here. Firstly, this is an unsafe block. Okay, because we're actually targeting memory directly, which is something we don't really want to do. Okay, but we can basically get through to those particular registers, and then we can basically flip them with read and write. All right, so we can write ones into them, we can write zeros into them, and we can read them. Okay, so this gives us the capability to actually manipulate and to control a chip. Okay, of course, this is very not safe. Why bother with Rust at all? This is not scalable. All right, it's not readable. You don't know that I'm actually toggling an LED on and off there. Okay, and it's really not maintainable, but it can be done. Okay, and this gives us a starting point. Okay, now somebody out there was very clever. And what they did was they basically said, well, if we've got that capability, right, why don't we just basically create another layer on top of it based on some sort of definition. And what happened was guys like the STM32s and the Nordics and the ARVs and all these guys that run these various different architectures, okay, what they did is they came out with these SVD files, right, which I can't remember what it stands for. But anyway, it's a big XML file, and it basically says, these are the registers, these are what they do, this is what you can read and write, and these are essentially how you flip them on and off, and this is essentially the bits and so on and so forth. And they got this all definition in a big XML file, so you can basically say LED 1 is, well, so not LED, but pin 1 is basically register E at block A, and it's basically bit 2. And that all gets that big definition. And then what you do is you feed that into this thing called SVD to Rust. And it basically produces this big generated piece of code for you, all right? And this big piece of generated code for you is called a pack, right? Which is a peripheral access crate. Now you've got access to a little bit better sort of control, right? So these lines at the top over here, you're going to see them again and again and again. Effectively, what we do is we basically get a peripheral. All right, and this looks a little bit complicated, but essentially, right, we get the peripheral, we take it, and that's an interesting one that actually will take over. There's a bit of history behind that. What that basically does is essentially behind the scenes is it basically says, if I take it one, give me some. If I take it again, give me none, which basically means is an option behind the scene, which means I have a singleton and I can only get it once. Okay, if I try to do this again, device peripherals will not have, well, if I try to unwrap it again, if I run that same course twice, it's going to actually give me an exception, or basically it's going to panic at that point in time because I can't unwrap something that's none. But this basically gives me a singleton that basically allows me to have device peripherals. All right, now this is essentially just getting the real-time clock and counter, and then essentially I can essentially get that GPIO. I can essentially get that GPIO, and then I can say GPIO, and I can essentially flip that bit. Now it's better. It's not quite right. I still have to know what's going on behind the scenes. I have to understand the registers. I have to understand how things are basically working underneath the stuff. Now, somebody who's working with an STM32 for years, they look at this and this reads like pure English to them, right? To guys like me who basically don't do that much work with STM32s, it looks like a lot of hard work and a lot of reference material. Okay, luckily, what we can do with this is we can essentially get another hardware extraction layer, and we can build on top of that. Okay, so this is effectively how this looks. You've got effectively two things. You've got the ARM Cortex, or essentially the chip itself, and then you've got, which has like GPIOs, the A to D converter, the digital to analog converter, which allows you to basically measure voltage levels and so on and so forth. And then, of course, you've got the processor, which has got things like the timers, something called a watchdog timer, which basically makes sure that the chip is not sitting there spinning in an endless loop. It basically stops it from doing that by crashing. And these two things go up to essentially the pack, which we just looked at, and the micro architecture crate. So you've got those two crates, and then essentially you can get out of that a whole crate. And now all of a sudden, you've got something which basically starts looking a little bit more sane, okay, and a little bit more easier to read and write. Okay, what we can do is we can go one step further and we can say, right, so effectively I've got a board over here, like an Arduino. It's got known peripherals. It's got an LED, it's got a button on it, and so on and so forth. And I can abstract that out and basically create a whole specifically for that particular board. And effectively, that's where you want to go. If you're effectively doing your own project, or you've got your own board that you're catering for, you're going to create your own hull to basically make it easy for you to be able to change things with it. Okay, so this is what it looks like at the end of the day. You can see that looks quite a lot different to what we first looked at when we were essentially flipping bits on and off. I get the peripheral, I get the GPIO, and then I basically set it to high or I set it to low. It's a little bit easier. Okay, so far so good. Yeah. All right. Now, when we basically are doing stuff on very small constrained microcontrollers, right, we want to limit the amount of memory that we're consuming. Now, when we are doing Rust on a computer, right, we are very fortunate and we're very lucky to have things like collections, such as maps or vectors or strings, which is these high-level utilities. But they take space. And when we're looking at a very small device, which only has a very small limited space, we have this option to basically say no STD, which basically means I don't want the standard memory in place. Okay. So what that basically means is that you get a much, much smaller, condensed, and very, very compact application that you can put onto your device at the cost of not having all that freedom to basically play around with maps and vectors and stuff like that. All right. However, there is something called heapless, which is a crate that allows you to basically put a lot of that stuff back. And they do some magic so that they actually keep it onto the stack and keep some stuff static. But so that'll basically give you the capability to get a lot of that stuff back. However, the ESP32, this is a beast of a microcontroller. The thing is an absolute monster, right? It can actually handle standard. So that's a very nice microcontroller to actually start off with, because you can actually have your hash maps and your strings and all the other stuff like that. Of course, you still make these massive binaries. You just need to understand that. So these are the guys that I have today. I'll start with this one, right? This big chip over here, that's an STM32. That's an ESP32. This is a new Raspberry Pi Pico, and this is the Arduino Nano. And I'm getting Rust to run on all of these guys, and we'll see exactly how that works. All right, so let's have a look at a couple of different stats. We'll just shoot through this very quickly. Now, of course, if I wanted to basically put all the stats in here, this thing would go all the way over there. In terms of things like if you want to compare apples with apples, how many GPIOs do they have? How much memory do they have? How much amperage do they consume? What's the current draw, and so on and so forth? How much voltage can they handle, and so on and so forth, right? But I'll just basically walk through them very quickly just to give you sort of a hello world type of introduction. The STM32, really, when we basically put it on this list, it's a bit unfair. And the reason why I say that is because the STM32 comes in so many different shapes and sizes. It comes from very, very small microcontrollers to incredible beasts that can run Linux on them. All right, so effectively, the first thing you want to do when you're actually going down the STM32 route is you want to basically say, what is it I want to actually build? What is my estimation of how much I need? And then essentially you find the chip that applies for that. So but the one that I have over here, right? This is a STM32F303. It's an ARM Cortex M4F, and the reason why I put that architecture over there is because that's effectively the Rust target that you need to find in order for you to be able to compile a language that will go into it. Right. This particular one has got 256 kilobytes on the flash. So if you're unfamiliar with microcontrollers, flash is effectively, we can think of it like the hard drive space that you can actually put an application into it, and it'll actually run from there. RAM, how much memory we have, right? Depending on the various different one that you got, it's got 32 to 512 kilobytes. I've got 512 kilobytes over here. And the clock speed is how fast it'll run. This one will run at 72 megahertz, okay? Let's compare that to this guy over here, the ESP32, right? This is not the most powerful chip, right? This is essentially the VROM. It's got 4 megabytes of flash, but it can be extended up to 8. All right, I've seen ones of 16 as well. It's got 320 kilobytes of RAM, which is significantly higher than a lot of the other ones over here. And it's fast. It's really fast, okay? And it costs about $5 on AliExpress, which is pretty impressive, okay? You can host web services on this thing. It's really remarkable what you can do with it. This is effectively a new kid on the block. This is essentially the Raspberry Pi Foundation trying to basically get into the microcontroller space because they've always been in the mini computer space. Right, it's got 2 megabytes of flash, and it's a great tool if you want to basically get kids to program and things like Python and show them how that sort of stuff works. Okay, it's got 264 kilobytes of RAM and 133 megahertz. It's not too bad. And then, of course, the Arduino Uno. Oh, sorry, the Arduino Nano, right? And it's surprising because that guy is probably the most well-known and most popular chip out of the ones that I've got, but it's a baby. It's got 32 kilobytes of flash. not a lot of space at all, 2 kilobytes of RAM, and it runs at 16 megahertz, right? Great if you're trying to do something really small and tiny. But yeah, we can still run Rust on it, which is pretty impressive. Okay. All right, so we're going to basically go through the STM32 project. How do we basically get the STM32 project? So you basically buy this board or a board like it, okay? And now you want to know, where do I start? How do I do this? So the first thing you do is you basically get some prerequisites. And I will basically be sharing this. I'll put the slide deck along with the meetup, right? So that you can get all the links and everything else like that. But you go to this link and it'll basically explain to you all of the things that you need to do, including all of these various different prerequisites, okay? So OpenOCD basically allows you to debug the thing. Well, that together with that allows you to debug it. The tool chain and QEMU is optional. That's basically a virtualized environment, which basically will run your code on your computer instead of having to dump it onto the chip. So you can actually debug it on your computer. It's like an emulator. And then we talked about the target. Well, here you see it, right? Rust up target add blah, 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 right? Somebody knows exactly what that means. And that's basically going to enable you to target these microcontrollers. And then you'll be able to write applications for them. Okay, so then you have the capability to actually run the Rust, but how do you actually start up a project? You can basically go cargo install, cargo generate, which is a really good utility. A lot of people are using it to basically create these templates to run Rust. And you put that command in, and you wind up with a project that's got everything baked into you, including automatic targeting and everything else like that. Okay, you do need to do some fiddling with this thing. You need to be able to sort of configure the memory. You'll have to basically figure out, based on your microcontroller, where the flash starts in memory and where the RAM starts and so on. And you'll need to be able to get the length, and then you set that. But this is all just sort of boilerplate stuff going through. And then you go to cargo.toml and you say, I want the STM32F4 or the F3 or whatever you want. And then I can show this to you in live. And then once you've done that, you've actually got a project. So let's have a look at a project, and let's basically walk through and show you some of these things that are interesting and unique to Rust projects. So the guys that are new to Rust, if you see something that you want clarified and you're not quite sure what it is or whatever, I'm happy to help you out as best I can. But I just wanted to show you this quickly. Hang on one sec. So this is essentially the project template. I'll just close this slot here. Can you guys see the text okay? Yeah? I can, yeah. Control. Okay. It's not as easy as I thought it would be. How about just FN? I'm just worried all the things connected. What I'll do is I'll just say zoom in. Kajang, how's that? Is that better? Can you guys one more time? Or is that okay? One more time? All right. How's that? All right. So first thing you see is the no standard command, which basically means don't want standard. All right. So yeah, I'm limited in terms of what I can actually do with this thing, in terms of vectors, heap, strings, and so on and so forth. Okay. Then I've got a whole bunch of use stuff. Okay. So I'll just basically go through to cargo.toml. So cargo.toml, if you guys are new to Rust, this is essentially where you put your dependencies and you say, I want to basically grab stuff off the internet that somebody else has written. And you'll notice over here, you've got this thing called the heap list, which is essentially allowing me to add in some of that capability like strings and heaps and so on and so forth. But the thing that we are interested in is the holes. Okay, and this is essentially where you find that. This is a hole over here, the STM32F3 discovery. This is the discovery board. So this is actually the discovery hole for that board. So I can actually target things directly. I can say I want to see like it's got like a tilt sensor on it. So I can say I want to see that tilt sensor, and I'll get the thing directly to it, instead of having to go through, well, let me get the I2S bus, blah, 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 blah. So that's essentially what that is. Okay, so that's hole. All right, so I'm basically using a whole bunch of stuff here. And then essentially we've got this stuff over here. Now, guys that have written Rust will probably not really recognize some of these things. So I'll just explain them quickly. Hash entry is basically saying, this is where I want this thing to start. At the beginning of it, I basically said, hey, there's no main. Then I basically said hash entry. And I basically called it main. But I could have called that banana, or I could have called that, start here. It doesn't actually matter. It's basically telling the the compiler to basically, this is where the beginning point is. And you've got this weird sort of symbol over there, which basically means this thing never returns. That's what that means. Okay, so that's once we start this application, it just basically sits there in a loop. It never ever returns, and that's what that particular symbol means. Okay, and this is an unfortunate one. I'm not going to show you this too much because this gets really hairy, but you will notice some things like peripherals, take, unwrap. Remember we saw that? You're going to see that all the time, right? But it is unfortunate that essentially we need to get the things like the reset clock and counter, and we need to basically put it back into the GPIO, split it up, blah, 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 blah. Don't worry about that. It's all boilerplate. Yeah. Yeah, yeah, sure. I'll share the stuff on Git as well. Okay, now we can see basically what we've actually been waiting for. Once we've got all this sort of business out the way, we can say LED set high, we can then delay, and this is essentially based on this clock stuff, so that's what all of that does. That stuff up there basically just gets me a counter for the clock. And then I can set low, and then I can delay again. And you'll notice that I'm getting little warnings over there, and that's because those things are actually bringing back a particular term in Rust called a result. Does everybody know what a result is here? Yeah. Has anybody not heard of a result? Okay, so a result is effectively something that you will learn very quickly in Rust, right? A result is essentially either okay or an error. It basically gives you a wrapper around one condition or the other. Okay, so in this particular case, I'm saying that everything's like hunky-dory. I'm not going to bother about it. But if it was going to error out, I could essentially catch that error, and then I could do something with it. Okay. All right, and then what's really nice about this is the fact that because I've got this built in, I can just go here. And with these boards, they've got probes built into them. They've got like something called a JTAG. They've got JTAGs built into them. So I can come in here, and I can effectively just press that. And it's going to go ahead and put a breakpoint in there and spin it up. And when it finally basically comes around, we basically get a breakpoint hit. And then I can basically play it. I can inspect variables, as you would expect. So I can basically have a look and see what's going on within the chip, etc. And then what I'll do is I'll basically just run this. And you see that it basically hits that breakpoint again. I'll release that, and I'll just show you what I'm showing on my camera here, which is over here. And if it comes to life, yeah, there you can see it's basically blinking. That's essentially what the code is doing at the background. I don't know, can't see it very well in this light. I can try and switch that on. That helps. Not really, because you can see it blinking, right? So yeah, there you go. All right, so that is the first one, the STM32. So I know that there was at least one guy in the that uses STM32s in the audience. Hope that was useful for you. Okay, so it gives you some sort of starting point. All right. Yes. Good question. Let me show you something here. Have you ever heard of, I think it's cargo size, is that right? Well, yeah. So what am I looking at there? 13912, it's tiny. Okay, so just under a kilobyte. Yeah, 1 over, yeah. That's in release, yeah. Okay. Yeah. 13. Oh yeah, you're right. Okay, but just also bear in mind, even though we have no standard in here, we still have the base crate. What is it called? Sorry? Yeah, we do have that, but there's something else. I can't remember its name now. There's another crate that that we have, and that basically defines things like a U8 int. It's essentially part of the preload. It's like a U8. What is a U16? What is this one? It's all that definition also gets dumped into the chip. Okay, I do find, to be completely honest with you, that the compilation at this point in time, I do find that the binaries tend to get quite big. And there are ways that you can basically make them smaller, but I think it's also just a very new technology as well. So hopefully it gets improved upon. All right, so back to the slides. All right, so that was the code demo. All right. Okay, so next we're going to basically look at my favorite chip, the ESP32, and we'll basically be spending a bit of time with this one because it's really done a really good job with the whole. Okay, so yeah, got some references there. Of course, you can have a look at those. Now, unfortunately, the documentation is just non-existent. I wouldn't say that you would criticize the documentation because you have to have documentation to criticize. So it's, yeah. But this is essentially a little story that happened to me. I went out and I basically followed all the instructions on how to basically get the target basically working on my laptop. And I basically spent more than 2 weeks falling flat on my face, just running into issue after issue after issue after issue. And I eventually basically came to the conclusion that I can't run this on Windows. It just doesn't work. And at that particular point in time, I thought to myself, I better get a Linux instance up and running. Now, there's a couple of options that you've got as a Windows user. Firstly, you can use something like Docker containers, right? But if you think that you're on a Windows computer and you're going to get a serial port to communicate out of Docker container, good luck. You're not going to get it to work. WSL didn't work, right? And I was worried because I've been using VirtualBox for years, but of course, right, what actually happened was when Microsoft basically came along and said everybody has to basically use WSL2 to run virtual machines or Docker containers, they completely broke VirtualBox up until recently, like 2 months ago. So thank goodness for that, because now I can actually run it on VirtualBox. All right, so in order for you to basically, so if you've got a Windows machine, get VirtualBox, run it there. Don't even try to run it on Windows. It's ridiculous. There is a ESP32 book. You can basically look it up on the internet. Rust ESP32. And what you're going to basically do is get a book and you think, great, I've got a book now, I'm going to be able to learn all about it. All it basically tells you is how to install the toolchain. That's it. And then the rest is up to you. So effectively, this is what you need to do. You need to go, and these are the instructions that you'll find over there. This is how you get essentially the target. And then, of course, you can generate the project in the same way. Okay, so you can see it's a bit of rinse and repeat here. Okay. And of course, we can use standard on the ESP32, which is kind of nice. Okay, but it does produce this huge binary. Now, one of the things that we have with the ESP32 is you've got this concept, or essentially this massive library called the IDF, which does everything. It basically does MQTT, message queue telemetry services. It does HTTP. It does HTTPS. Man, everything that you can think of that you would want to do out of this chip, right, the IDF will cater for you for it, okay? And what they do is they effectively take the Rust binaries and they effectively have a sort of a bridge between the Rust binaries and the IDF. And this particular project template, unfortunately, I don't know why they decided to do this, but every time you actually say cargo generate with that particular command and you say cargo build, it basically downloads the entire IDF into that project. Okay, so it is a dog ticket building. It takes like 20 minutes to actually build it. Okay, on a virtual machine with one CPU. But you know, once you get it going, of course, you don't have to build it again. It's pretty fast after that. Okay, so let's have a look at the actual template. So now I'm going to basically go to my VirtualBox. But before I do that, I actually just need to plug this guy in here. All right, and now we're going to spin up that virtual machine. You guys doing okay here? Are you guys tracking with me? Yeah. All right. Hopefully we get a bigger screen than that. Let's see. All right, so this might take a minute or two to warm up. I'm sure it'll be fine. Right, so this is just running Ubuntu. And what's really nice about VirtualBox is the fact that you can actually forward your serial ports out of it, which is kind of nice. I don't know of any other technology that does it as well, honestly. So I'm hoping for a bigger screen. It's bigger, it's not brilliant, but I think it might do. Maybe we'll get something better. I'm basically recording. I've got quite a bit of stuff running on this machine, so it's being a bit slow, but we will get there. See if we can actually get it bigger. That's a little better. Okay, good. All right. So, see if I can zoom in because that's very small. Oh. That's not what I thought it would be. This is basically, sorry guys, just give me a second. Just going to open up the right project file. And just be patient. Come on. Recent. Yeah, probably. All right. So hopefully we actually are getting somewhere now. Yes, that looks good. Okay. I will try to zoom in again, just so that you can see what's going on. Zoom, because that is very small font. I'm assuming you guys can't read that. Now, so I wrote a little bit of an application on this, okay? Just to basically show you some sort of, just rather than just a flashing LED, I wanted a bit more. Can you guys read that? Or do you need it more zoomed in? Yeah? Okay. How's that? Is that better? More? All right. Zoom in. It's very slow. How's that? Is that better? Okay. Is that okay? Yeah, can you guys see that? I'll just basically highlight some of the things. So you notice over here, we've got this weird result over here. Have you guys ever seen that before? Okay, that's a result with just no error condition. It's coming from a particular library called Anyhow. Anyhow is a really nice library. It allows you to basically wrap up any error into its own type. So you don't wind up with all these sort of mismatched error types when you're trying to return. And it allows you to do things like this, saying just return whatever, so that's kind of nice. You notice that it is returning something, not just returning nothing or not returning at all. So over here, you see this again. All right, I'll just zoom in here one more time. Come on. All right. You see this peripherals equals peripherals take unwrap? This is my singleton of my peripherals again. All right, and then essentially I get peripherals pins GPIO2 into output.unwrap. So there I have my LED, okay? And then I can basically work with it, which I'll show you just a bit. So essentially we can see that a good old Rust compiler is just kicked in there and we can see essentially stuff. Now, I just wanted to show you this very quickly. So you got Rust, if GPIO2 over there into output. If I basically say GPIO, let's say 38 into output, you can see I've got 38 there. But if I say 38 into output, when we finally actually get the Rust analyzer to kick in, it's going to complain to me and say to me, no, this is not legal. You can't do that because it's only a valid input. But the Rust compiler, of course, is being nasty to me and is not proving me all wrong. Anyway, we'll go through that in just a moment. Hopefully it'll catch up. All right, so what I'm doing over here is I'm basically checking a button. All right, so I'm going to basically say match button is low. If it's okay, then it returns a state. If it's an error, it'll panic. But if it's okay, it'll break out of here and it'll basically go into this loop. I'll show you this in, what it actually looks like. It then prints out info. So you've got these really nice ways to print things out, setting high, setting low, and then it's going to connect to the internet and basically download the Google page. All right, and I can show you that over here. I don't want to get into too involved into all the nitty gritties, but what you can do is you can basically say, all right, I'm just basically setting up a Wi-Fi connection access point, and then going to basically go out and connect to this particular hotspot. So I'm going to basically make sure that that's turned on. And then I'm going to create this thing called a Wi-Fi client. And then the Wi-Fi client is going to go up to Google, and it's going to fetch it, and then basically dump it out on the screen. So I thought to myself, I know that's a lot to take in. I don't expect you to understand all this code. I'm not trying to, show you all the bits and pieces, but let's have a look and actually see something work. So there's a couple of things that we would be interested in actually seeing here. Let's just firstly go back to main.rs and just see if this thing actually has caught up. It hasn't. I'm not sure why it hasn't. But anyway. I'm going to make that 2 again. All right. Usually it does. It complains to me when I'm not trying to demonstrate it to other people. It says, no, you can't do that, but it's doing it now. All right. Now, have you guys ever heard of just files? Just files are the most awesome thing out there. They're awesome. They're really cool. So a just file is kind of like a CMake file. You basically create this you download it, and then you can create complex commands like that, and you can just say, just flash, and it goes ahead and writes it up for you. Very nice. So that's what I'm going to do here. All right. I'm just going to say just flash. Okay. It is very small. Grab this. Okay, so it's building, and this does take a little bit of time. It's essentially compiling it. Even though it has recently built it, it's running very, very slow, much slower than it usually does. Probably because Zoom is involved and what have you. But we'll give it some time, and then maybe we'll have a look at it in just a bit. Maybe while it's busy doing that, we can have a look at the slides, and we'll come back to it while it's doing this, and then we'll see how it actually looks. It's okay, so that's there. There's a lot of stuff going on inside here. One of the things that I actually passed as one of those parameters is essentially the partition table, which is very interesting. So the partition table over here is essentially a CSV file that basically says, this is my big 4 megabytes of flash. How do I want to carve it up? And you can see over here that I basically said, all right, I want non-volatile storage to put over there. I want essentially the factory to be able to be put there. And I said a factory app, that's my application. I'm allocating 3 megabytes. I didn't have to. I could have basically put a file for just general utility storage, or to store audio files or video files or whatever. And I have done that in the past as well. So we can basically specify how we want to carve this thing up, and we have a lot of options, all sorts of things like, do we want to basically use the whole HTTPS bundle that comes with these things, so that we can actually go through to HTTPS sites and certificate bundle. It's crazy what you can do with this thing. This actually thing is going on quite well. You can see it's basically dumping that into the chip, but it is quite a lot of work that it's doing. So yeah, while that's busy, let's continue a little bit with the slides. So we talked about anyhow, we talked about the peripherals, and also with the log macros, we saw that info with exclamation point. We can go warn, and we can go error, and it gives us nice color-coded output on our terminal. All right. So that was the code demo that we did. And the next one we're going to look at, and the last one is going to be the Arduino. Okay. Just before we do that, let's just have a look back here. See how this guy is doing. Okay, there we go. So you can see it says button state false. That's what it says. Okay. And then I'm going to press the button. Oh, that was the reset button. Button state false. And then it says, all right, going Rust demo, and it's going 1, 2, 3, 4, 5. And now it's basically going to connect to the internet. It's looking at the beacon frame. It's connected. It's got an IP address. It's basically going up to the HTTP client. And I don't think we actually saw that, but there is Google homepage. So of course, that doesn't have to be Google homepage. It could be JSON from anywhere, you know. So very easy to actually work with services and so on. Yes. This one was huge. This one was massive. It does actually tell me. I think it's just over 1 meg, 1.5 meg. So it's big. It's huge. But that's the whole standard library, you know? Yeah. I mean, from a microcontroller perspective, that's massive. Okay. But if you want the standard library, that's what you're going to pay for it. Yeah. All right. Now I'm just going to open the next one. All right, and then back to the slides. All right, so very similar, install the prerequisites. You need to install this thing called RaveDude, and then essentially you generate the project. So you've got your ARV, yeah, just before that, right? You've got the ARV cargo stable install RaveDude, and essentially what you're going to get out of that is you're going to get the target. And then once you got the target, you can basically then get a project template. And once you've got the project template, right, you can basically generate the project. And you can imagine what the first couple of lines look like. Let's go ahead and look at that again. Where is it? One sec. Where is my, I've lost my output. Where's my output? 1 second, guys. Yeah, you're right. Thank you. All right, let's try this zoom in thing again. I really like the way that these guys did it. It's super simple. Okay. So here you can see again, no standard, no main. You can see the entry. You can see the fact that it never returns. And look at that peripheral. Man, that's simple. All right. You get the peripherals, you unwrap it, and then essentially get your pin out of the hole. Really easy. And then you can basically, you get your LED, you get your serial out of your Arduino hole, and then you can essentially set it to whatever serial you want to actually communicate to. And then essentially you've got this LED toggle, and we're just basically printing something out over there. All right, so again, really, really straightforward and very easy. And if you think I can remember how to actually flash it, I don't. Actually, I think it might just be cargo run. Let's try that. Oh, no, it's in port. So I think it's cargo run. I can't remember how to run it now. Cargo run, anyway, I might come back to that. But anyway, let's just try this once. So it'll be dev. I'm not going to basically waste your time. You can imagine what this does. In fact, it's running on here at the moment, so it's flashing. Yay! So like I'm not going to get into the whole. So yeah, it does work. I must say that these guys did an incredible job on making it really simple, and I'm really wishing that STM32 guys could do that too. Yes. Yeah, it's big. 6 kilobytes, I believe. It's huge. Mm. I think you can, but also you can, if you're really that constrained, you can go down to the pack level, and that's going to basically, then you're talking, registries and bits and binaries, and yeah, then you're really constrained. That's going to give you something that's going to be very similar to writing assembler. Yeah. Yeah.
So if you did want to constrain yourself, you can just modify the pack yourself and rebuild it.
Sure.
Wow.
It's all open source. So of course yeah. So you could do that
easily.
How good are you? Yeah. Yeah. All right. So now the next one, this is the last one. I'll just basically wrap this one up and then we can go to questions. So the next guy is the Raspberry Pi Pico. Now there's two different versions that you get, the Raspberry Pi Pico and the Raspberry Pi Pico W. And the difference is that the one has got wireless, the one that I doesn't. But they're fun to play with. They're good fun to play with. Now you might have noticed with the ESP32, I didn't bring a probe, so I couldn't debug it. I couldn't put breakpoints in there. So just for guys that are new to microcontrollers, if you want to debug something, usually what you have to do is you have to put an extra peripheral attached to certain pins. And this basically controls the way that the program counter inside there works and gives it commands to basically stop, or you can inspect memory and stuff like that. And usually you need this extra hardware. And you do get, the ESP32 does work with standard JTAGs. You can buy them off AliExpress for about $10. So that thing plus the JTAGs, about $15 for a kit. What's interesting about the Raspberry Pi Pico is that you see this rat's nest over here. It looks like a rat's nest, all sorts of things. It's two Raspberry Pi Picos. The one is acting as a probe. So the one is basically a debugger for the other one. And that's, so it's very easy to actually do that, well documented. And yeah, that's quite helpful. Okay, and then essentially that's all the various different layouts and how you basically connect it up. Okay. Of course, then what you're going to do is you're going to basically install the prerequisite. This is essentially your target, your Rust target that'll basically do the generation for you. And you basically get these other things that'll allow you to do things like the probing and so on and so forth. You generate the project again, and you basically show the demo. So let's go have a look at that quickly. So there's the STM32. Let's just go into the other one. This guy is a little bit hairy. It's got quite a bit of boilerplate going on. But you'll notice the same sort of similarities. So no standard, no main. You know what that means. Effectively, you start in here. You notice the same things. You basically get the pack. You get the peripherals. You unwrap it. You get the core peripheral, which basically give you things like the watchdog timer and the timing, all right, the essentially for clocks. And then essentially this is setting up your clock. It's basically giving you the right megahertz and everything else that you need. That from there you can basically get a delay, and then you can essentially get your bank of pins. Okay, I'm just going through this really quickly. And then finally we can basically pins.led.push into output, and then essentially we get our pin. And then we basically also have this info that will give us debug statements, and we can toggle these things on and off. Of course, because we also have a probe, I can debug it, which is nice. If I get the right connection. Okay, so let's see if this works. Should just work. So of course, Visual Studio Code, these templates come with all the various bits and pieces that you need to debug them, which is kind of cool. So a lot of the hard work and a lot of grunt work has been done for you, luckily. I do find, and you'll basically notice this now, that when you actually do debug on this thing, if it decides to work, let's try that again. No probes found. Oh, that's because I got it plugged into the other one, not the probe. That's why. Let's try that again. Okay. So main.rs, we should actually hit that breakpoint now. There we are. So we've got that breakpoint. We can basically step through it. One thing I did notice is that as you try to step over it, it tends to basically take the program counter and put it into weird places like that. So you got to just basically be a little bit finicky and finesse your breakpoints so that you can actually catch them and just figure out what's going on. And part of the reason for that, I mean, that you often see when your applications compile for release. So that's kind of the cost that you get for that. But yeah, you can actually still sort of just follow logic bugs and still print things out and actually get things to work. So you can see login info on, off, and so on and so forth. So if you are interested in microcontrollers, or if it's part of your job, or you want to basically get into Rust, there is this basically way of basically having these generators that do give you quite large compilation files, and I'm pretty sure that's going to improve over time. This is a very new tech. It's only been around for a couple of years, and it's all so all of the stuff that we're seeing, all these generations and all of these halls are effectively done from the community. None of it has basically been done from anyone else. So that's probably why they are not as mature as some of the other tools we have for some of the other languages out there. However, still, if you are a Rust developer, it's really worthwhile looking into, because I can tell you from personal experience, right, that the majority of microcontroller bugs that you get out there are memory-based. And the problem is, particularly with microcontrollers, is once it leaves your office, you know what the rest of the story goes. Somebody's going to lose money and somebody's going to complain. So if you can avoid those sort of mistakes, it can make a big difference in your life, even if you're at the moment having a little bit more complexity, or actually just chewing up a little bit more of that very precious flesh that we all love so dearly. All right, cool. Thank you very much for listening. Just one thing I just forgot to mention for you. This is my wish list for the future. This is my wish list. I wish it was less confusing. I wish it was basically a little bit simpler. I wish it was more unified halls, and I wish there was easier documentation. The SP32 group have put together essentially an embedded hall, and they're hoping that everybody tries to go into the bandwagon with that. Because of course we're sitting in Rust. What does that mean? It means we get zero cost abstractions. So all we have to do is actually create the correct traits, and we need to effectively imply those traits, and we should be able to actually produce the same code base that could then scale and port to any microcontroller. That's the dream world. We're nowhere near there yet. But yeah, that would be nice. And then essentially part of this is essentially Rust slides. There's, if you guys are very heavy into the microcontroller stack, there's something called Arctic, which is a really interesting sort of project that's coming along for real-time interrupt analysis. There's FreeRTOS has already been ported, and you can probably run just about every single microcontroller under the sun out there. And if you've got the right target and you want to basically write some of your code in Rust and some in your C, there's bindings to be able to go backwards and forwards. So there's a lot of stuff out there. It just takes a bit of research, and yeah, there you go. Thanks, guys. So yeah, any questions?
Have you played around with any RISC-V microcontrollers like the ones from Sci-Fi?
Not for that one, but I have played with the ESP32C3, which is a RISC-based microcontroller, and it's really easy to control. And what's really nice is the new ESP32C3 has got a built-in JTAG. You can actually configure, because it's got a USB built-in, it's got a built-in probe, so you can actually debug it straight away. It uses a lot less gimmicks and finicky stuff than the regular ESP32 because it's a RISC-V. The port to to Rust is much more straightforward and much more supported. Yeah.
And a follow-up. In general, what do you think about RISC-V? Do you think it's a promising platform having an open ISA like that?
I think it is interesting. So just to put, I'm pretty sure like a lot of guys are new to microcontrollers. So I'll just lay the land out very quickly. So when you basically are playing with something like this guy over here, the STM32, okay, STM32, right? They own these microchips, or they sell you these microchips, but they don't own the architecture. The people that own the ARM architecture is the ARM Cortex guys. It's a separate company. They don't produce microchips, but they basically produce all the patents for it. So what happens is every single time somebody buys one of these microchips from STM32, part of that fee goes to a royalty. And that's how essentially the ARM Cortex works. And it's the same thing with your Apple computers, and it's the same thing with your Raspberry Pis, because they're all ARM Cortexes. Okay, so RISC-V is a new one, right? Essentially a reduced instruction set. And the promise, or essentially the hope, is that it's an open source platform that these vendors like STM32 will then be able to utilize, like x86, like x60, like the Intel chips and so on and so forth. And what that basically means is that there's not going to be any royalty anymore, which basically cuts out that middleman, which basically reduces prices. And but we're still a little bit away from there. I think that the future is looking good for that. But I also think that people like Extentia have definitely, I mean, not Extentia. Extentia is one of these architectures. Like Espressif have really jumped on the bandwagon with that. I haven't seen any RISC-V STM32s. And I think the reason for that is just simply because, personally, I believe that there's probably a heck of a lot of IP that they've got. And there's a huge amount of documentation and so on and so forth that they would have to essentially revamp from scratch almost. So that's probably why we haven't seen such a big movement. But I do think that you're probably going to see a lot of competitive players in the market. Yeah. Also, the other thing about RISC-V processors, which is interesting, as long as with the extensions, is they don't seem to be suffering from the chip shortage. We can still get those. You can't buy STM32s in the moment. I don't know, like it's weird. So yeah.
You mentioned teaching.
Yes.
You do teaching with C.
Yes.
I found getting into systems programming with Rust much easier than C because of all those memory errors and stuff way back. But how far off do you think microcontrollers are to being able to be used for teaching? Microcontrollers with Rust.
It's a good question. It's a really good question. There's two things that will need to happen in order for it to be teachable. It needs to be simplified. So I think that with some of the hulls, we're already there. So like with the Arduinos, those hulls and the ESP32 hulls, it makes it possible. And you can actually go out, and there's a company called Ferris Corp that effectively created a Rust microcontroller course for the ESP32. It's the only one I've seen out there so far. But I think that if one of the biggest problems, I think, right, personally, is that if you look at anybody who's serious about microcontrollers, it's STM32s. It's STM32s, it's Nordic, and those are the core ones. And their Rust holes are terrible, honestly. They're just really hard to deal with, and there's just no documentation. So, there has also been some community that I saw recently. Somebody actually tried to make sort of a unified hole that is very simple. So there's potential moving in that direction. I give it another year or two. I think we'll probably get there.
So it's more of an ecosystem and cross-pollination. The good ideas from.
Yeah, and then somebody just needs to basically get up and say, all right, I think it's worth the risk. Now, I can tell you from experience now, right, with my own course, right, it's not a small investment. All right. Now, one of the things that you don't want to do as a teacher is you don't want to basically get committed into producing a course that's going to take you 2 years to actually produce. And then all of a sudden, by the time that 2 years is finished, the whole ecosystem has changed, because that's going to happen. So this is my course over here. All right. You really, so I personally wouldn't actually start doing Rust on the chip now, not in any serious fashion. This is, I think it's nearly 24 hours or 25 hours worth of course content on this. I would never do that with Rust because I know that I would have to redo the entire course every 6 months. So yes, it needs to settle a little bit. And I think it will. Yeah. Any other questions? Yeah.
Actually, I want to ask, for example, we are using the C++ on a really safe environment.
Yeah.
Say, for example, we are using ARM because in comparison to RISC-V or something, it's much safer, reliable, and it's really tested, to be honest. But in the Rust application, to be honest, we can't find something which is reliable in the libraries. Actually, you can't find, let's say, STM32 F4 series, for example, HAL for these sort of things. There are two things, actually, lack of the libraries and beside that, I think the reliability of them. How do you predict that in future? For example, what is the main options of these sort of Rust in comparison to C++, which is much safer?
Well, I wouldn't say that C++ is safer. It depends on what you mean by safer. You mean there's more chance of having the peripheral libraries that you require and the holes that you require. Is that right? Is that what you mean?
Yeah, exactly.
Yeah,
yeah. For blinking analysis, you are not writing code. For example, changing the register in every line. Just mentioning maybe in header or something.
Well, look, I mean, look, I think when you come to STM32s, okay, specifically with the STM32s, all right, it really depends on what you're trying to actually produce and what is it you're trying to actually build. Remember that effectively with the STM32, you can always fall back to the pack, the peripheral access crate, which is effectively giving you the same thing that you'd have to basically build your own hole. But if you can't find a hole out there, then that is always a fallback. And of course, if you've got the pack for that particular chip, then anything that chip can do, including USB, Bluetooth, whatever it is that chip can do, you've got the pack level to do that. But that basically means you're digging in the documentation. At that particular point in time, you probably think to yourself, well, once I get to know it, I'm just going to basically put an abstraction or a layer around it. At that point, you've got yourself a hole. Now, whether or not you share that with the community is up to you. But that's effectively how these ecosystems grow. Yes. Not with Rust, no. I'm still a neophyte, as I said. I'm still getting my head around it. At the moment, I just, what I do for work, right, is I basically do a lot of protocol analysis. So I effectively look at a lot of Wi-Fi packets and a lot of Bluetooth packets and stuff like that. And I actually need to decompose them and actually figure out certain elements and look for certain patterns within them. And what I'm finding is that Rust is a really good tool for that. And what I'm actually finding, because I mean, a lot of the stuff I do is in Node.js, and we're sort of trying to transition into Rust, and we're trying to actually sort of build these modules, because Rust can actually be plug and play into any of these Node modules or any of these other things. So yeah, that's kind of where I'm going. Sorry, what was your question again? Maybe I didn't answer that. Yeah. That's right. Yeah. Yeah.
Commercial ones, no one does it. No one works.
Well, there is work being done on them. The problem with Arduinos is they're just too small. Now, the reason why I was telling you about what I do is because when I'm done with that, yeah, we've got essentially a crate there. And that's essentially something that could be utilized anywhere. So people can generally create these holes, and you'd be amazed what's out there. I'm currently actually working with a Realtek, one of the Realtek devices, because it's one of the only 5 gigahertz devices out there that can actually talk 5 gigahertz of the Wi-Fi. And believe it or not, there's a target for it. There's a hole out there for it. So yeah, why not? Yeah. Okay. Any other questions? All good. Well, thanks once again. Oh yes, sure. So yeah, it's a good question. Okay, so I don't understand or know exactly what the philosophy is behind that. Okay. There you go. Thank you. Cool. All right. Good. Any other questions? Well, guys, enjoy the pizza and beer.